Okay, so good morning, everybody. So today I have the honor to host Mario Salluzzo as a speaker. So Mario Salluzzo is research director in the laboratory at the CNR-SPIN. So CNR, well, you know, is the National Research Council in Italy, and SPIN is devoted to, if I remember well, superconductive, oxide, innovative materials, right? Yes. So Marco Salluzzo, well, you follow the research on oxide interfaces mostly, but not only, also superconductors, I think you have worked. So he's widely recognized by the work on transport and structural characterization in oxide interfaces, and especially in relation to the emergence of two-dimensional electron gases. He has worked a lot in many archetypical systems like LaSTO, and also lately in other variants. I think you will talk today about some variants of this LaSTO and also potassium tantalate, other oxide interfaces, right? So he has made very original contributions to this research regarding, as I said, transport, superconductivity, and also other functional properties. And today he will address specifically how to engineer these interfaces with different functionalities, right? So just, just to add that Marco will be around here until Thursday, right? So if you feel that you would like to talk to him, let me know, or just address directly to Marco. So feel free to contact. So thanks again, Marco, for accepting giving this seminar, and please, the stage is yours.
Thank you very much, Gervasi. Yeah, I'm very happy to be here, also doing an experiment, actually. So it's very interesting for me to be here. This first time I am at ICMAB. I'm impressed about the people which are here. I already knew some of you, collaborating with you, but I mean, for me, it's a pleasure to be here. So I'm going to talk about a way to try to modify the functionalities of oxide two-dimensional electron gas. I will try to present mostly new results that have been, some of them published, some of them are completely new, and in order to try to. I will make also a recap of past activities, and before I starting, I would like to especially thank people that contributed to this work. Particularly Yuchen, which is here, brilliant researcher at SPIN Naples, and Bertrand Rat, is Marie Curie postdoc. And of course, this work was possible only thanks to the many collaboration using different experimental and theoretical approach in order to understand these artificial interfaces. I don't have time to mention all of them, but I would like to, in particular, underline the contribution Julien Brehin made a PhD on artificial ferroelectric oxide to DEGs in the group of Manuel Bibes, and all the people working different synchrotrons for the studies. Some of them I'm going to present. And Manish Verma is a brilliant theoretician working in the group of Rasesa Pencheva in the past. Then he moved, did many DFT calculation, and etc. Then, of course, I have to mention the theory group in Naples and in Salerno doing a very nice quantum transport calculation on devices based on these oxides. So this is outline of talk. I will just briefly mention the introduction about the LaSTO and some of the heterostructures we have realized in the past few years. I will be quite brief on this part because I would like to focus on the new results obtained by Martin Dorat and by Yuchen, which are concerning ferroelectric 2DEG and 2DEGs with engineered inversion rotation time reversal symmetry braiding. Okay, what is the motivation of our activity that was in the past? Essentially, we are interested in symmetry breaking phenomena in general in the two-dimensional materials. And everybody knows this a sketch we did was inspired by other some review paper. So the idea is that when you combine spin-orbit coupling with two-dimensional material, you can, in principle, think about spin orbitronics and quantum topological electronics devices. These are a few examples of devices being proposed. There are many more. Some of them already exist, like spin-orbit torque memory, made, for example, with topological insulators, not only. Also oxides, and spin-orbit qubit also been realized and working. Then there is hope to realize the topological qubit one day, and many other possible devices. So we are essentially interested in combining materials which are essentially two-dimensional or quasi-two-dimensional, which exhibit a tunable spin-orbit coupling and possibly different ground states, and try to combine all of them, in particular ferromagnetics, ferroelectricity, and superconductivity. Because we believe that if we are able to do that, we can access to novel physics and novel functionalities to realize the devices in the framework I described above. And for in the last maybe more than 10 years, I mean, I started to study the oxide two-dimensional electron system. It was discovered 20 years ago. There is a superconducting two-dimensional electron gas formed at the interface between band-insulating oxides. And all over the year, we have fabricated some kind of artificial electrostructure, like ferromagnetic and superconducting to DEG, which show all the signature of multi-ferroelectric behavior. And more recently, we focused on these one-on-one heterostructures, where the physics is particularly different. I have to mention that recently, more recently, in 2021, were surged interest in the oxides because there was discovery of superconductivity with TC of 2.2 Kelvin and the KTO11 interfaces. This is also a very interesting system that now is more studied, I mean, is, let's say, very much studied, and is promising also for application, particularly, I would say the topological superconductivity in this system is quite possible. Let's now go to the topic of today. So we start essentially from the LaAlO3 system. We combine these two band insulator. Just a few words about the properties of LaAlO3 or 1,2 DEG. The physics is the one of bands which are originated from titanium 3D T2G orbitals. But due to the confinement, these orbitals, these bands are split. The splitting is about 50 millielectron volt, and so by tuning the Fermi level, one can access single band or multi-band physics, which is also an interesting property. But what is, from a functional point of view, maybe even more interesting is that the superconductivity already in 2008 was discovered, and it's possible with this system to get a full superconducting to insulated transition using the gate voltage. And not only this system feature quite strong Rashba-Spinobel interaction, which was not completely expected, which is also tunable. This is a magnetoconductance measurement, which is one way to study the contribution of spin-orbit coupling. So it's a system where you can have superconducting to insulated transition with gate voltage and also tunable Rashba spin-orbit coupling. This is already a very interesting platform, for example, for spin-orbit qubit. Now, at the beginning, we started to modify the properties of this LaAlO3 to introduce spin polarization. And we essentially decided to use this delta doping, so essentially replacing or depositing between strontium titanate and lanthanum aluminate an epitaxial few layers of europium titanate, which is isostructural to STO, but has a magnetic moment. Europium is a magnetic moment of 7 more magneton per atom. And by DFT calculation, it was demonstrated that 2DEG is formed essentially in the europium titanate layer, and the titanium states acquire a finite magnetic moment, which is stronger in the europium titanate, but also is present in the few layers of STO where essentially 2DEG is located. The bands are completely split, spin up and spin down band, so it's essentially spin-polarized 2DEG. Indeed, it shows both titanium XMCD signal, so this is a measurement of magnetic moment, and the europium XMCD signal. System is essentially a ferromagnet with in-plane AC axis. And the effect of these magnetic properties is reflected in the anomalous Hall effect. This Hall effect data is showing an anomalous component, which can be tuned by the gate voltage. But also, what was surprising is that the system also undergoes a superconducting transition. With the TC, which is slightly lower than more or less half that one of LaAlO3 system, so it's very exotic, I would say, two-dimensional electron gas, spin-polarized and superconducting. To introduce ferroelectricity, some colleagues have proposed the use of another approach, essentially depositing a lanthanum aluminate on a bulk calcium-doped strontium titanate with 1%, 2% of calcium doping the bulk strontium titanate becomes ferroelectric. And by doing so, you can grow a lanthanum aluminate or other oxides, like aluminum oxide. You can get a 2DEG, which is essentially ferroelectric. I mean, show a coupling between ferroelectricity and the transport properties. That's to be more precise. And the coupling is demonstrated, for example, by looking at the sheet resistance as a function of temperature of the 2DEG, which show at the ferroelectric transition a clear change in the slope. And then at low temperature, you can perform, for example, resistance versus gate voltage measurements, and you will find that essentially there is like a ferroelectric loop with non-volatile change of the transport properties. Then it was natural to combine this approach and this approach to get something which contains both ferroelectricity, let's say, in the bulk calcium-doped strontium titanate and magnetism in the europium titanate. This was an idea of Manuel Bibes, and that also was part of the thesis of PhD thesis of Jeremy Breen in his group. So we have realized in Naples these heterostructures, which grows quite well, together with Duchenne, actually. And this heterostructure feature anomalous Hall effect, in plane magnetoresistance hysteresis, and again a coupling between the sheet resistance and the ferroelectric transition. And maybe more importantly, if you perform a gating experiment along the ferroelectric loop of the bulk calcium-doped STO, you can measure the anomalous Hall effect component and the magnetoresistance. You can see that there is a modulation of the properties, but the modulation is non-volatile, because if you come from P down to P up polarization, you see that the change of the anomalous Hall effect and magnetoresistance is non-volatile. I mean, zero gate, you can get a non-volatile change of magnetotransfer properties. More recently, we performed a very complicated experiment, X-ray absorption spectroscopy, in particular X-ray magnetic circular diagonal measurement with the gate voltage applied, so in situ. And we essentially found out that both the orbital moment of the europium and the spin moment of the europium is modulated by the polarization, also in non-volatile way. You can see that there is a change in non-volatile in the system. So this is a demonstration of direct magnetoelectric coupling between the two ordered parameters. Now, coming more to the new results, there is the problem of calcium-doped STO is that the TC is 25 to 30 Kelvin maximum, and the polarization is relatively low, ferroelectric polarization. So it would be much better to have a system where the polarization is much larger and possibly with the room temperature for electricity. So another approach is to use another layer, a ferroelectric layer deposited between lanthanum aluminate and strontium titanate, which is ferroelectric, and try to get a two-dimensional electron gas and couple the polarization of the ferroelectric to the properties of TUDEG. So this is the content of the activity of Martin Dorat doing this Marie Curie, one of the part of his activity. This KNN is potassium sodium niobate, is one of possible well-known piezoelectric and ferroelectric material that can replace lead titanate, so lead-free ferroelectric, because it has a very large polarization and a very large TC, ferroelectric TC. So we try to follow this approach, but there is a problem. The problem is related, let's say, to the physics and that leads to the formation of the two-dimensional electron gas. While there are many reasons why TUDEG forms at the lanthanum aluminate strontium titanate interface or interface between, let's say, any band-insulating oxide polar and strontium titanate, one of the mechanisms which is certainly playing a role is the so-called polar instability. So when you grow along the O1 direction, an ionic compound like lanthanum aluminate on a neutral, formally neutral planes like TO2 layer of STO, there is, by increasing the thickness of LaO, a clear increase of electrostatic potential energy that will be accumulated inside the lanthanum aluminate film. So if the thickness overcomes some threshold, essentially there should be some kind of reconstruction, because otherwise the system is not stable. So there are various ways to eliminate this polar instability and avoid the polarization catastrophe by, for example, chemical substitution, for example, disorder. But one mechanism that is certainly playing a role is the transfer of electrons from the surface to the interface, which means that TUDEG is formed at the interface in order to solve the polar instability. It's not the only one playing a role, but certainly it's playing a role. And I would like to underline that a TUDEG electron gas is formed only in this case if the interface is titanium oxide, lanthanum oxide. Strontium oxide, aluminum oxide interface does not form a two-dimensional electron gas. In the case of potassium niobate on the top of STO, the problem is the charge of formal charge of potassium niobium is completely different from the charge of lanthanum and aluminum. In particular, potassium is 1+, and you can clearly see that if we grow directly potassium niobate on top of STO, even if it's paraelectric material, essentially you have exactly the opposite charge compared to the case of lanthanum oxide, titanium oxide interfaces. So this system can be, the polar stability here work only if actually holes are transferred to the interface, not electrons. On the other hand, it's very known that in this oxide, in particular the strontium titanate, basically TUDEG is not formed when there is hole doping. I mean, an hole two-dimensional electron gas is very difficult. Two-dimensional system is very difficult to be realized with this strontium titanate. So this is not the way to get TUDEG in this system, apparently. On the other hand, if we are able to realize strontium oxide terminated the strontium titanate and grow KNN on top of this, we have a situation which is similar to the case of lanthanum aluminate on STO. In that case, polar catastrophe can be eliminated by transfer of electrons to the interface. Of course, we don't know exactly if the electrons goes only in titanium 3D states, can go also in niobium 4D states. This is one important difference. But apparently this can work. Then if we add the ferroelectricity on top of that, if the system is ferroelectric, we have another degree of freedom. the polarization, of course, will add up to the charge which is transferred to the interface. So if the polarization is up or down, you can favor or disfavor the formation of 2 DEG. In particular, if it's down, there is an increase of charge carriers transferred, electrons at the interface. If it's up, on the other hand, there is a decrease of this charge density. So these are very simple, let's say, description of the system. Luckily enough, there are also DFT calculations. The systems are quite old. In 2009, there were DFT calculation exactly on that system, considering essentially 2 kinds of interface. One is the interface between strontium oxide and niobium oxide, so the interface which favors the formation of 2 DEG, and the other one, the opposite interface. And from this calculation, it's practically clear that there is also from final table that it's only when we have this configuration, essentially, we can have 2-dimensional electron gas. And from the point of view of minimization of the energy, it seems that the system, when the interface is strontium oxide and niobium oxide, wants to have the polarization down. So these are the theoretical predictions. Now let's see to realize experimentally all this. It's quite complicated. So first of all, we tried, of course, to grow LaO on top of KNN on TO2 terminated STO, because TO2 terminated STO you can buy directly, so it's very easy to get TO2 termination. But the gas is insulated. There is no formation of 2-dimensional electron gas in that case. If we, on the other hand, grow an epitaxial strontium titanate between the single crystal TO2 terminated STO and the KNN, we can get a 2-dimensional electron gas. And the reason why this happens is because essentially there's a switch of determination on the film. On the film, the determination change from TO2 to strontium oxide, and the determination is complete when essentially you have about 10 units of STO on top of your epitaxial STO. This depends also on the deposition condition, but in our deposition conditions, which are high oxygen pressure and 750 degrees with positive laser deposition, you can also see this switching during the grow, because you see the oscillation, rate oscillation, which with the appearance of another periodicity, which is related to the other termination. Okay, then we performed in situ XPS to verify that the strontium is in excess at the surface. But the final word was that essentially this, the high-resolution transmission electron microscopy on this heterostructure, show indeed when we grow an STO on epitaxial film on top of a single crystal is niobium oxide, strontium oxide interface. So it's a nice result. And this one is conducting, as you can see, is a 2-dimensional gas. From the point of view of the grow and the morphology is very nice, as you can see. I just would like to point out the in situ XPS show the formation of, so the transfer of electrons not only in titanium 3D states, titanium 3+, but also the presence of some niobium 4+. So in principle, also electrons are transferred in niobium 4D states. Of course, we don't know at the moment if these niobium 4D electrons are contributed to the transport. But I mean, this is what we obtained from XPS analysis. And finally, we performed some characterization to understand if the KNN is ferroelectric in the heterostructure. Since in order to get a nice heterostructure, we need a layer of KNN, which is maximum 10 unit cells, so it's very thin. We should rely with we should use technique which don't have the problem of leakage current, essentially. So one technique is the piezo-force microscopy. Probably all of you knows the technique, but it's based essentially on writing or switching locally the polarization of the ferroelectric. If the material is ferroelectric with the gate voltage, you can write these nice patterns. And you can see this is the PFM phase image that there is a clear, nice change of 180 degrees of the phase between region written with a voltage on the tip of negative voltage and positive voltage. And you can also see that without applying the gate voltage, essentially we have the same phase of having plus 10 volts. So this means that the polarization is pointing down, the spontaneous polarization, which is the conditions which favor the formation of the electron gap. Then you can, for example, do some local spectroscopy. You see the classical loop that suggests you the system is ferroelectric. Then we perform also other measurements. For example, R versus T of the 2DEG up to high temperature. We found the signature of the ferroelectric transition at the right temperature in the transport properties. Then our colleague Andrea Rubano performed some second harmonic generation measurement, which suggests that there is at least a component of the second harmonic generation signal. A second harmonic generation signal is present when you have non-central symmetric material or there is a breaking of symmetry. There is at least a contribution from non-central symmetric KNN because the signal increases with the KNN thickness. This means that the KNN is clearly non-central symmetric, which is a condition to have ferroelectricity. Okay, now I will switch to the last part of the talk, which is the activity of UCHEN, some part of the activity of UCHEN. Is about the study of another kind of interfaces, an interface where we are switching the orientation of STO to 111, and we try to introduce in this in the 2DEG also spin polarization by growing also europium titanate in the system. Okay, the material grows decent way. We can grow nice heterostructures. And also show ferromagnetism at both the europium edge and titanium edge. Again, with in plane AC axis. Here is not very well clear the hysteresis. We perform a squid measurement to have a clear signature of the hysteresis in the magnetization. And so the system more or less shows time reversal symmetry breaking and the spin polarization like in the O1 LaAlO3 STO system. Now, why these 101 heterostructures are interesting? Are interesting because if you look at this perovskite from along the 111 plane, the surface looks like have essentially an hexagonal symmetry, and essentially the system is similar to bilayer graphene. I mean, this was already observed some years ago. There was a Nature Communication paper suggesting that many oxides, perovskite can host, let's say, exotic physics if grown along the 1-1 direction. And more recently, there were in particular two papers from the Cavia group, which studied the non-magnetic 101 LaOSTO2DEG, and they found very interesting properties. In particular, if you consider just a very simplified physics, a minimal model where you consider just a pair of Kramer's band, so just single band picture with the Rashba spin-orbit coupling, and you apply a very strong magnetic field in the plane, essentially two Rashba split bands are crossed at finite momentum, is well known. And due to the trigonal symmetry of the system, this gives rise to a gap along the particular direction of the Fermi surface. And due to that, the Berry curvature of the system is completely non-trivial. There are hot spots, which give rise to a non-trivial Berry phase. The Berry phase is really determine most of the many properties of this two-dimensional electron system. And non-trivial Berry phase that is different from zero, which is the one you can get in disordered metals without spin-orbit coupling, and different from pi, which is essentially the Berry phase of a two-dimensional electron gas in presence of spin-orbit coupling. I mean, that's trivial. In principle, with application of very strong in-plane magnetic field, you get non-trivial Berry phase, and this is one of the consequences is the presence of an in-plane anomalous Hall effect. Another one is the second order nonlinear in-plane transport due to the quantum metric, which is very exotic property of condensed matter system. However, to be everything described in this simple picture, you need that the bands, these Kramer's bands are well separated from all the others. You have to work in a single band regime. So you need the trigonal crystal splitting between the lowest band and the highest band, which is very important in the physics of this system. On the other hand, one of the problems is that we measured actually a long time ago the trigonal crystal splitting of the 1,1 LaO-STO and also our 1,1 LaO-TO-STO. And we found out that the trigonal crystal splitting is very small in the 1,1 LaO-STO. More or less, this was confirmed also from soft X-ray angle-resolved photoemission experiments. Just I will show the band dispersion, which is very different. In the case of 1,1 LaO-TO-STO, where we see a clear trigonal crystal field splitting between these two bands, while in the 1,1 LaO-STO, the splitting is very small, so it's very difficult to really work in a regime where there is only one band contributing to the transport. So I would say that while very interesting, the results of published on 1,1 LaO-STO, for sure their interpretation is some inclusion of the multiband effects, because for sure the more than one band are at play. On the other hand, in our LaO-ETO-STO system, for structural reason, we are lucky, because the trigonal crystal field splitting is quite large. So really we can tune the Fermi level, for example, only in the lowest band. And in this case, if there is no time reversal symmetry breaking, if the system is non-magnetic, the physics is a trivial physics of a two-dimensional electron gas. Even if this is a plot of the Berry curvature. I don't know if you are familiar with that, but this Berry curvature essentially along the Fermi surface, which the Fermi surface of this system has this warped shape, is hexagonal. In some sense, is not trivial, but if you calculate the Berry phase corresponding to this Fermi surface, you get values which is pi. So this is a two-dimensional electron gas with the Rashba spin orbit splitting. So it's standard material. So essentially, 1,1 LaO-STO, we expect even the presence of this trigonal, larger trigonal crystal field splitting, there should be no the Berry curvature should be, the Berry phase should be trivial. But in our system, there is a time reversal symmetry breaking, because we added the magnetism in the system. And when this happens, essentially in zero magnetic field, so without application of any magnetic field, we should have more or less the same physics that was described, I described before in the 1,1 LaO-STO in presence of strong magnetic field. So essentially, we have a system which is like a type 2 Weyl semi-metal. And here, if you do work out the calculation, which actually were being performed also by Yuchen, it's very good guy in doing even calculation. You have more or less the same physics, but at the zero magnetic field. I mean, you have an intrinsic magnetization. You get hot spot in the Berry curvature, and this corresponds to a non-trivial Berry phase, which is not neither zero neither pi. And what is interesting is that there is a very easy consequence of this non-trivial Berry phase that you can measure by performing magnetoconductance measurement at low temperature. Measure the magnetoresistance or the magnetoconductance as a function of the magnetic field. In a standard two-dimensional electron gas or in a metal without spin-orbit coupling, you expect the Berry phase is either 0 or pi. When it's 0, you have usually weak localization mechanism for change of magnetoconductance. When it's pi, you have a weak anti-polarization quantum correction at low temperature. This is very easy, very well studied, many material, works very well also for oxides. You can fit the data very well in the, when this situation applies. But if you have non-trivial Berry phase, which depends on, the, for example, on the magnetic gap, in our case, it depends on the magnetic gap, the magnetoconductance is completely different shape because it's a competition in the same range of magnetic field of weak localization, weak counterization terms. It is a consequence of the opening of the gap at the Dirac-like point. And I have to underline that this kind of physics has been developed in case of topological insulator with the magnetic or with the gap at the Dirac point. And indeed, if you perform measurements on standard 2DEG, you get classical weak polarization or weak counterization magnetoconductance, so you can fit very well. While if you look at literature, for example, in this magnetically doped topological insulator, you start to see this anomaly in the magnetoconductance, which is similar to what I have shown before schematically. So essentially, this weird shape with the maximum some kind of field. And this is exactly what happens now in the case of our two-dimensional electron gas. So in our oxide two-dimensional electron gas, we saw essentially the same anomaly, which can be tuned by the gate voltage, of course, very pronounced. And to fit this data, we should rely on a formula which is very simple and have been actually worked out for topological insulator with the magnetic gap or with the gap in general, where we have a contribution from weak localization and another one from weak anti-localization. And this formula works quite nicely. You can fit the data very well. And so this is the first thing that probably our system belongs to this category of type 2 semi-metal, and everything is related to the non-trivial Berry phase. Now, another proof that this is probably true is that we performed also temperature dependence measurement of this magnetoconductance. And when we cross the ferromagnetic TC, that this system is relatively low, it's between 6 and 8 Kelvin usually, the anomaly disappear and only weak anti-polarization remain in the magnetoconductance correction. So we believe that this system is an example of where Dirac-like fermions are formed in spin-orbit coupling split bands in presence of time reversal symmetry breaking. Just to summarize, this is the situation for oxides in general. This oxide two-dimensional electron gas. This kind of graph is, if you perform measurement on LaSTO01, LaOTO-STO01, and also in LaSTO111, essentially you get magnetoconductance correction which are trivial. The one you can explain with the weak polarization with anti-polarization theory. And only in our case you get this anomaly that is due to the non-trivial Berry phase related to the presence of autospot of Berry curvature along the Fermi surface. So this is a summary of the talk. I would just like to mention that I had no time to go in details in this on this topic, but if you have questions about in particular the multiferroic 2DEG, I can answer you very easily. And so I would like to thank for your attention. Thank you very much.
Thank you very much, Marco, for this plethora of results and very interesting results. So now we have time for questions. So you have any question, please raise your hands, or people online, if you have a questions, also drop your question in the chat line. Okay,
Thank you for your talk. A question about the part of the combination between the interface of the two-dimensional gas and the ferroelectric that, if I remember correctly, was potassium sodium niobate. You have shown PFM results that if we consider that this is due to ferroelectric switching in the niobate layer, it means that the polarization charge must be compensated by the two-dimensional gas when you go from negative to positive applied field with either negative or positive charge in the two-dimensional gas. The question is if this is compatible with the scenario of polar catastrophe.
This I don't know. In the sense that, in principle, when we switch to negative, since we, at the moment, we don't have an estimate of the polarization charge, because this needs to do a test, ferretic test analyzer, so we don't enter. According to what should be the polarization of KNN, in principle, we should destroy the TUDEG. In that case, if the TUDEG is destroyed, then you cannot switch back. But if you look, so that's important. At the end, if you at least at room temperature, even the system which is according to our analysis, when we go KNN on TO2 terminal STO directly, it's true that you get an insulating behavior, but still some conductivity remain. So it means maybe it's not a metal, the screening is not effective, but it's still enough to be able to switch again. To be honest, I think the polarization catastrophe can never be considered, in general, the only mechanism working for these oxides. For sure, for example, oxygen vacancies in lanthanum aluminate in particular plays a role. And what I can tell you is that at least we have done another experiment I didn't show, which was the time dependence of the amplitude of the PFM signal over time. This classical method to understand if you have just charging. For example, you can have just charge localized, you write charge, or there is for electricity, and over 4 days, the change of amplitude was 20%. So in our opinion, is this behavior of good for electric? But if alone is not enough. Alone is not enough. And this is the reason why we performed these other experiment and also the second harmonic. Then maybe we'll try the ferroelectric test analyzer. This we'll try, but I'm not sure it will work.
Maybe more simple is that considering the system physics of the two-dimensional gases, it's simply impossible to switch completely a ferroelectric layer, no?
Impossible, no. I think it's possible because it's
both directions. I am not speaking only
in both directions.
If
the polarization is very strong, it's like that. You destroy the TUDEG because theoretically, if you let me show maybe another picture I have. But in the TUDEG, if the confining electric field has one direction, if it's electron carriers, and then the ions, even in the LaAlO3, no, they form, they move down. The titanium ions move down far from the interface. Let's say the oxygen goes toward the interface because there is a confining electric field. So this is a dipole. Electrical dipole. In LaAlO3, this electrical dipole is not non-volatile. You cannot switch and if you change the gate, it's not volatile. In order to switch completely the polarization, inside the 2DEG, you should have the ion that goes up. But if it goes up, it means the electric field is reversed. In that case, you don't have a 2D electron gas. You should have maybe an all gas, but it's not possible. So you are right, absolutely. Indeed, our goal is to try to write, locally the 2DEG. That's the original goal.
Okay, thank you.
Ciao Marco, thanks for the beautiful overview. The questions also related to this topic. Two more material science question. Why potassium niobate or potassium sodium niobate and not barium titanate? And why you still need lanthanum aluminate on top? Why you still cap the potassium? Plays a role or does not play any role? Because you discussed the polar catastrophe in respect to the potassium niobate.
Lanthanum aluminate is an amorphous layer. We grow it because the potassium niobate is not stable in air. So you get water. So that's important.
Okay, it's amorphous.
Yeah, it's amorphous.
Regarding barium.
About the barium titanate, yeah, we have done that. We have done that, but it seems less robust. So, for example, I will show last slide. I had a slide about that. Sorry, let's see. Ecco qua, this one. Yeah, we have now there is a paper accepted on nanoletters by except in these days. One problem is that with barium titanate, it seems to be difficult to the piezo force microscopy is not working well. Let's say it's not so we're not sure. Actually, we are not sure that it's a ferroelectric barium titanate, at least at the thickness that we are considering. So we know that it's polar because we see XLD signal, we see also second harmonic generation signal, etc. So for sure it's polar, but it is ferroelectric in the sense that you can switch. We don't at the moment we are not sure. But you can use barium titanate. It seems to be not. I don't know why KNN seems more robust from the point of view of electricity. And that's our experience about barium titanate. And there is another thing that in barium titanate, for sure, the 2DEG forms inside barium titanate. While in KNN should not be present to 2DEG.
Yeah, but that was actually the next question. Then the 2DEG will really form within the ferroelectric layer, right? Because then the whole discussion is always about the electron gas is ferroelectric. Okay, it's polar. Like one thing is to have like a proximity effect in which you have a ferroelectric layer that is next to the electron gas. Here, the 2D electron gas will be potentially within the ferroelectric matrix.
Yeah, this is the same problem we have, for example, with calcium doped steel. So is that a proximity effect or is really ferroelectric? With the barium titanate, I don't know, because we could not do the switching. So maybe we had to do, maybe if I do an experiment trying to switch the polarization, but it's not easy because you have to do switching from the top. Experimentally is challenging. With calcium and steel, I can tell you that at least there are dipoles that we switch in non-volatile way, because we see that there is non-volatile change of the orbital splitting, of the titanium 3D splitting. So the X3D change in non-volatile way, but it's not full. You just change a little bit. So it means that the polarization is still have one direction. So you don't change completely. And it's the component, some component which is which dipole. You can call that ferroelectric. I don't know. We call it ferroelectric-like, let's say. But at least it has a really a non-volatile effect on the properties, on the ionization, transport property. In that case, you should have the metal, which is ferroelectric. I will say that it's still not, even there are people that, I mean, probably a metal can be ferroelectric if the screening is not good enough. Yeah, in some sense. But if this form, let's say, disordered phase, because another possibility, you have, or it's an homogeneous, let's say, ferroelectric-like material, I'm not completely sure. That's I think it's not clear because there are many reports, even barium titanate bulk, that there is ferroelectricity and metallicity, even superconductivity at the same time. But it's difficult. So I mean, it's an open question, that one.
Thank you.
Okay, more questions?
Thanks very much for the very interesting talk. Forgive me if the question's stupid or impertinent, because I'm not from this area at all. But I was kind of attracted to your AFM image where you showed all the steps. No need to show it. I mean, I'm sure this is common in the area. But you talk about 2D materials, and they obviously are. But there's an awful lot of kind of step edges, aren't there, always in this kind of material? So what kind of effect do they have on the bulk properties, if at all? And what kind of proportion are there of those edges? And does the interface kind of propagate perfectly over that step edge?
Okay. Yeah, if I understand well, you are so the question is that is very, very relevant if, in particular, the 2DEG is really two-dimensional. Okay, these are not two-dimensional, are quasi-two-dimensional in the sense that the confinement, which is a few nanometers, so it's not one layer. The confinement is in comparison to, for example, to the mean-free path, it's a smaller mean-free path, and the superconducting coherence length is smaller. So it's it's more correct to say quasi-two-dimensional. It's not really two-dimensional, but if it would be two-dimensional, of course, step edge will. What I can tell you is that step edge have an influence. Have an influence. Usually, if you make grow this material on subsets with a very high vicinal cut with many step edges, you get an isotropic transport just because of the step edge.
More questions? I have one question. Maybe you can clarify. Is you talked about the relevance of having the picture of one single band in the trigonal field in a 111. So you show that there is these ARPES measurements, I think, and in the conventional 111, well, conventional in the sense that you have only LaO-STO 111. Apparently, this single band condition is not met. Is that correct? So in that case,
yes, this is my opinion.
Is your view? Oh, okay. So explain maybe your view, because this, you know, a couple or years ago or 1 year ago, I can remember now, in the group of Geneva and Cavilla, they reported this nonlinear transport, and the picture basically was one single band, if I remember well. Is that correct?
Yeah, this single band.
Then this nonlinear transport could equally arise from multibands? Well, I don't know.
Yeah, can come from multi-band, this for sure. So I think it's very complicated because this morning I read again the quantum metric paper from Cavilla. And at the end, most of the effect they see is written in the paper. They see when they cross the second band pairs. even in a picture where there is a trigonal crystal field split, because they put a trigonal crystal field splitting. So I think it's complicated, this story. For sure, so we have now two independent measurements that suggest the trigonal crystal field splitting 1,1 LaAlO3 is small. Let's say 10 millielectron volt. I would like to exaggerate. And typically in this model, they use the splitting. They take actually the splitting that I found on the 1,1. So they use this paper, let's say. They use the trigonal crystal field splitting we found in LaAlO3. This Caviglia, also Daga, I don't know why, but they use that one, which is between, in the paper was 20 millielectron volt. Now we know that it's a little bit larger, because I mean, the gamma point, at least. So for sure, these models are very, so we know because Yushen did the calculation, depends a lot on trigonal crystal field splitting. When you start to put other bands, is a mess. So if it's a mess,
yeah,
probably all the effect will be enhanced, because every time you have anti-crossing between two bands, typically the spin-orbit coupling is not anymore Rashba-like, is a cubic, and then is enhanced. We know from 0,1 LaAlO3, typically Rashba spin-orbit coupling is enhanced when you cross the Lifshitz point. And probably, I think that this comes more from these anti-crossing points, these non-linear, which for sure is interesting, okay? It's interesting physics, but the model is not correct, in my opinion. And for some reason, in the 1,1 LaAlO3 works. But if we go to very large gate, for example, the experiment we are doing now, we are working at positive gate, for sure we need multi-band physics.
So your view is, if I understand correctly, is that even if the trigonal field is small, if you have multi-bands, the anti-crossings together with the spin-orbit coupling can give rise to the kind of nonlinear transport, but it's okay. I mean, the experiments are like that.
Experiment, okay.
But the model with a single band with large trigonal would require
you will require using a full Hamiltonian with all the bands, and then you have to put the Fermi level there and calculate the contribution. So also
to explore this kind of physics, putting European titanate should work, no? According to the ARPES experiment.
This was just luck in some sense, because there is some distortion in the different titanate which makes the band split.
Okay, thank you, Marco. So I don't know, there are no questions online. Questions here? Last opportunity? No? Okay. Well, thanks again, Marco.
Okay, thank you very much.